tehnica ultrasonică fazorială. Domnul Edwin Van Der Leden de la Eddyfi va face o prezentare a echipamentelor foarte puternice capabile de această tehnică. Edwin.
Thank you, Christian. Welcome everybody, my name is Edwin Van Der Leden. I work for Eddyfi Technologies as a technical expert for phased array UT and MFL and guided waves. I have two presentations for you today, so it will be two hopefully half-hour presentations, one on the phased array and one on the guided wave. So first we will start with the basic principles of actually advanced phased array applications. So if we have a look at what we're going to talk about, first of all, we'll have a look at ultrasonic phased array by itself, but also some newly developed technology around phased array, which is called FMC, PWI, TFM and PCI. What these are, I don't know how familiar you are with UT, especially phased array, but we'll explain this to you later. A current trend is that there's a lot of development in UT phased array, and FMC PWI is one of them, and TFM PCI is one of them. But to understand the difference, we'll go into the basics. So this is only the basics. Then we'll have a look at some products, both supporting the FMC, the PWI, TFM and PCI for the Mantis Gecko and the Topaz series. We'll have a few case studies and then the pros and the cons and some conclusions. We have a setup here which is currently live, and I'm going to try and show you on the screen as well. The nice thing is with the Gecko and the Mantis range that we can connect remotely, and this is something you can also do in the field. So if you have somebody in the field using the equipment, we can remotely connect to the equipment and help out the person in the field while he's doing an inspection, or in this case, as we do a presentation. So first of all, if you look at the current play field of ultrasonics, now ultrasonics is very broad, and you can see ultrasonics being used everywhere in the industry. You can think of radar installations for following airplanes, or you can talk about sonar systems for tracking ship movement. And this all falls under ultrasonics. So first of all, let's have a look at guided waves. Guided waves is an implementation of ultrasonics where we actually use low frequency ultrasonics to detect defects in pipelines. We have a nice setup over there. I'm not going to go into the details too much because we have a separate presentation on this, which we'll discuss later. In general, we use low frequencies, and it's very much a screening technologies where we look for corrosion that is developing in mainly pipelines. It's an in-service inspection, so it does not require assets to be shut down, and therefore very valuable as a screening tool, which further requires follow-up on normal UT, phased array or conventional. Conventional is the ultrasonic method that we probably know the most. It's been around for more than 40 years, and we use it on a variety of applications. Mostly high frequencies. We look at either wall thickness measurements, trying to detect and size corrosion, or we use the technology to try and detect defects in welds. So both longitudinal waves and shear waves are currently being used. If we look at shear wave, for instance, with conventional, then typically we use 2 to 3 probe configurations, a 45, a 60 and a 70, to try and find the optimum angle of reflection compared to the defect in a weld. But it is also limiting us, because if we do conventional UT, we're going to have to move the probe to make sure that we have full coverage over a weld. And this is something that we're trying to, or that we avoid with phased array, making phased array far more efficient than conventional UT. On the other side of the spectrum, we also have TOFD. TOFD stands for time of flight diffraction. And TOFD, basically we use a very broad angle probe, introduce a lot of ultrasonic energy into the material, and what we are looking for is tip refractions. With those tip refractions, we actually can use to do very accurate sizing of defects in welds. So what we see normally is that when critical welds are being inspected, we both use conventional UT plus TOFD to make sure that we find the defect and very accurately can characterize defects. So TOFD used quite a lot in conventional, but also with phased array. Then if we have a look at phased array, so with phased array we're actually trying to be more effective when we do, for instance, weld inspections. So instead of using 3 different probes at different angles and moving the probes, we are now capable of using a single probe with an aperture that we steer individually. We can create each individual angles within a range. So we don't have to move the probe anymore, and we have all the angles between, say, 30 and 70 degrees. And we call this sectorial scanning, so it's much more efficient. The other thing we can do with phased array is have 2 probes from 2 sides. So we don't need to use the different probes with the different angles on both sides. No, we can use 1 probe setup, as we have here, 2 probes, and scan a whole weld in one go while we record the data. In traditional phased array, you can see a nice setup here on a pipe. We use delay laws, and we can have either linear scans or sectorial scans, or combine the two, which is called a compound scan. So conventional phased array has been in the market for quite a few years now, and you see that the development is further advancing in terms of excitation of the modes. As you can see here, a nice setup allows you to have a look at how am I doing my inspection. Am I actually covering the full volume of my weld, and therefore will I find most or all of the defects that are currently in the weld within the specification. So if you look at an ASME specification, it will tell you that there's a certain amount of defects allowed or not allowed, which can either be an accept or a reject, and that's actually what we can see here in what we call the scan plan. So the scan plan will allow us to create a full setup, look at the data, and then make sure that we have a complete coverage and make sure that we find most of the defects available or that are present in the weld. Now, I don't know if you follow the development around phased array, then you might have heard about FMC. FMC stands for full matrix capture. But also there is HMC, which is what we also call the sparse mode. And the sparse mode is actually not using full matrix capture, but only an individual set of sensors. And then there's also PWI, which stands for plane wave imaging. Now FMC and these are all excitation modes. So this is the way we introduce the ultrasound into the material. So full matrix capture is where we actually use the full array one by one. So we have one exciting element in an array, and arrays can be 16, 32, 64, or even 128 elements inside a transducer. As you can see here, the setup that we currently have here in the system is a 32 element, but you can see the larger probe there is a 64 element. Now with FMC we're only using one element, and we're firing with this one element, and then we're recording with all the other elements. With sparse, we're going to leave out a few elements, and the advantage of that is we increase speed, because if we have to fire and record on all those elements, it's going to take a lot of time. It's going to create a lot of data. So we want to save data and we want to save time, so we can inspect a weld rather quickly. Another mode is PWI, and PWI is plane wave imaging. That basically means that we're using the full, in many cases, the full aperture instead of one, to fire the ultrasound into the material. But we're listening with each individual element one by one. The advantage here is that we lose a little bit of resolution, but we gain a lot of productivity. So where you see that an FMC excitation mode can be rather slow, very, very high resolution, but rather slow. On the other end of the spectrum, we can use PWI, where the inspection is much faster. There's another advantage of PWI over FMC, is that if we only fire one element, the amount of energy that we can get into the material is rather limited, because we only have one element, and the angles are, the beam spread is quite high. With PWI, we use a wavefront, and the wavefront creates much more energy because we use the full aperture of the transducer, meaning we can inspect also thicker thicknesses. Okay, so how does this work? Sorry, I have another slide here. So this is the excitation mode. This is how we get the energy into the material. The other thing is we need to reconstruct that energy that we receive back into an image. And that we can do next to the normal traditional phased array. We can do this with TFM, which stands for Total Focusing Method, and PCI. PCI is Phase Coherent Imaging. I will show you a little bit about the differences. The reason why I'm telling you this is this is the new boss in the world of phased array UT. So all the equipment that we have here that have TFM capabilities will also allow you to do both TFM and PCI, will both allow you to do full matrix capture and plane wave imaging. The big difference between TFM and PCI is that TFM is a amplitude-based imaging reconstruction method. So we basically look at certain points. I'll have a few slides on that as well a bit later on. Please help me for time, guys. I don't know. I don't want to overdo the thing, but and then we have PCI, which is basically looking at phase. So we're not looking at amplitude, but we're looking at phase. The big advantage there is that even the smaller defects, regardless of amplitude, regardless of size of the reflector, will give us a very nice high contrast image of the defect. Again, this is what I just told you. Full matrix capture, FMC, partial firing of the FMC is called HMC or sparse. And then we have plane wave imaging, full aperture, a lot of energy. And then on the imaging processing side, we have TFM, Total Focusing Method, and PCI. And I will give you a few examples on how this is valuable in day-to-day applications. Okay, so first of all, the excitation mode. As we can see here, I don't know if I can get a pointer up here as well. Pointer. If you look at this part of the image here, you can see that one by one the elements are fired. So one element is firing, and then one by one all the individual elements are receiving. Then we're going to move to the next element, and we're going to do the same. So what we're actually doing is we're creating a matrix with quite a lot of A scans. So instead of, we look at traditional UT, we now, where you have only one A scans, we now create an A scan domain. And in this A scan domain, in this case, if we have 464 elements, we create 4096 A scans from which we can gather data. So what happens next is that we're going to reconstruct an image based on the data that's being collected for each of these A scans. And how do we do that? Okay, so that's just later. We're still in the excitation mode. So plane wave imaging works a little bit different. So instead of having one element firing, again we have the full aperture firing, which basically is dividing the number of A scans by 64. When we fire the PWI, the plane wave, the full wave, we're going to reconstruct the image, or we're going to save the data on exactly the same way. So we're going to have, in this case, not 64 times 64, but we have 10 different angles. So what we're going to do with plane wave imaging, we're going to shoot in a few angles at the same time. So instead of 64 times 64, in this case, we chosen 10 pulses or 10 angles, reducing the number of A scans down to 640. So you can see there's a big benefit there in A, the amount of data that we have to save, and B, the speed in which we can collect and process the data. Again, so if you look at plane wave imaging, we have much higher energy. and we have better signal to noise ratio because of the higher energy. We can go up to higher pulse repetition frequency, PRF, meaning we can increase the scan speed by 3 to 5 times, and this is for TFM. We'll have a look at TFM later and how this can be valuable. And also we have significant smaller file sizes, as I've said before. So this is all on the excitation modes. How do we get the actual energy, ultrasonic energy, into the material? The second thing is, how can we restructure that energy that we receive back into a valuable image? So first of all, there's TFM, is total focusing method, and we can use total focusing method with either FMC or PWI. This is basically how it works. So we have an image, and we're gonna calculate the image based on each individual image within a pixel, and we can choose the pixel size. Obviously, we can choose 10 pixels, we have very low resolution, but we can also choose up to 1,000,000 pixels, so it makes the resolution very high. Obviously the scan speed goes down, but the image resolution is very high. So again, what we're going to do is we're going to create with TFM, we're going to create a matrix in the area that we want to inspect, and this can be a weld. So TFM can also be very valuable for weld inspection. And we pick a point which we call point P, and for point P, are we moving? We're gonna look at the specific A scan, which is a combined A scan of the series of the transducer. We're gonna combine those into one A scan, and then it's something what we're gonna do is called time picking. So we're gonna have a look at a specific time here, as you can see, on the A scan, because I know the travel time there and the travel time there. I can actually determine in my time of flight where that exact point is within my matrix, or within my A scan. Then I'm going to extract that specific point for the combined A scans all together and create a new point for that specific point in a matrix. And we're going to do this for all. So in case of FMC, we're going to have to do this 64 times 64, 32 times 32, so it's quite a lot of data. So FMC with high resolution TFM can be relatively slow, but will allow you to look at a defect in quite high resolution. We're going to do this for all the transmitters and all the receivers. So we're going to get a new image for each individual point within that matrix, and this is how that image is actually look like, right? When we reconstruct it based on all that data. But this is amplitude based. So as we've seen here earlier, we're basically looking at the amplitude. If there's no amplitude, if there's no reflection, then obviously we don't have any results there, and it will be a blank pixel. The other thing we can do is phased coherent imaging. With phased coherent imaging, we're basically looking at the phase rather than the amplitude. So it doesn't matter how big the reflector is, we're going to get either a plus or a minus, a positive phase or a negative phase. It works rather in the same way in terms of image reconstruction, but what we're going to have to do first is we're going to have to use an algorithm which takes the original amplitude-based A-scan signal and turn that into a phase image, right? So we're going to have to relay a phase, so either plus or minus. And it's called the Hilbert transform algorithm. Don't ask me how that works. I'm not a mathematician, but obviously it works. So when we've done the Hilbert transform, this is what we're going to get. And there's a few areas where we can identify. So this is your initial pulse, where we can see the phase there, and we can see a small defect there, for which we see the phase there. Now what we're going to do is exactly the same as with the TFM. We're going to look at each individual time of flight for each individual pixel. Again, we have pixel P. We're going to calculate the time between the transmitter and the receiver, and then we're going to do time picking, not on amplitude, but on the phase. And then we're going to do that for 1 pixel, and then we're going to end up with all the pixels. If we reconstruct that image, we're going to get something which looks like it's similar to what we've seen with TFM. However, there are a few advantages. And this is the nicer one, the nicer example, which I wanted to show you. So if we've done that, if we do a comparison, then here what we see is PWI, so it's plane wave imaging combined with total focusing method. It's an amplitude-based image of a weld. And as you can see, the defects are quite small. Maybe my gain was a little bit low, so but never mind, we're always looking at a reference. But as you can see on the left side, that image, the images of that defect doesn't really stand out. Because we're looking at amplitude, we're looking at a range of different values which we're displaying on the screen, depending on your analog to digital converter. On the other hand, we have a PWI PCI image, and all of a sudden you can see that those defects are much more clearer to see. It's because the value of the image is now only 0 or 1. It's a phase, or -1 or +1. So it's a phase, and because we're looking at phase, the image of the defects in the weld are much more clearer to see. So the detection range with PCI is a little bit higher. Does it work for everything? No, because it's very unreceptive to circular defects. What it's very valuable for is planar defects. So if you have a lack of sidewall fusion, you have 2 tips, and those tips basically transmit ultrasound themselves because they're being hitting with ultrasound. So they're going to transmit ultrasound themselves, a little bit like TOFD. And that's why you see a higher energy level from the PCI. Also, there is a downside. You have a little bit more noise with PCI because we're only looking at -1 and +1. So even noise is either -1 or +1, but we can filter that out. So what you see with the PCI is a filtered image. Okay, so traditional phase array, and I think that's where we want to continue from now with the presentation. But I wanted to give you this information on FMC, PWI, TFM, and PCI. It exists. We can do it today. All our equipment is capable of doing this, and it can provide. And this is the phase array of the future, right? Definitely phase array of the future. So then, if you look at our product offering, the product range, we have equipment in different categories. We have entry models, we have the portable advanced range, and we have the high-end inline systems. So if you look at the entry models, this is called the Mantis. We don't have a Mantis here, but Total Control will have one to show you. This is an entry model where you can do phase array, you can do TFM. It's a bit slower. We're limited to a certain thickness. You can do PCM, but not with too large arrays, and a single group. So if you look at the Gecko, the processor in there is faster. We have more channels available. So this is a 64-128 TFM, 128 meaning we can do a 128 aperture TFM on 64 channels individually. So it's a full 64 channel architecture, which many of the systems do not have. Also, we have the Topaz series, the Topaz 16, 32 and 64. As you can see here, the Topaz 64 is a high-range piece of equipment, very suitable for having multi-groups, working with scanners for exotic materials. You can think about stainless steel inspections, thick materials, mainly used in the nuclear industry. While we see that the Gecko application is more used in the field of airplane component inspections, as well as weld inspection. We also have the remote units. So first of all, let's have a look at the smaller ones. Like I told you, this is the Mantis 1664, can do TOFD, TSM, is fully compatible with all the standards, so ISO, ASTM, and EN. Up to 6 probes, 8 groups, Very nice piece of equipment. Can also do conventional UT if you want to, but then of course the equipment that Waygate is offering is much more cost effective for that, but it can still do it. I'm not going to focus too much on this. Obviously it's normal weld inspection, also corrosion mapping and elbow inspections using scanners or not if you want to. Then the Gecko range from 32-128 up to 64-128 depend. So you would choose more channels and a larger aperture if you have thicker materials, more channels if you want to increase your productivity by using multiple probes in a scanner. Again, this unit is capable of traditional phased array UT for TOFD, for TFM, and also compatible with all the standards. It's the model that we have here. This is the 64-128. So come and have a look, and we can have a demonstration later on. Then the Topaz 64, like I told you, is a high-end model. Again, in 32-128 up to 64-128. The software is a bit more advanced than what we see with the capture software. So for very specific applications, the Topaz is really a fantastic piece of equipment. Then we have called the RDU, the remote data acquisition units. These are inline inspection units. 5 minutes left? Okay, I'm gonna have to speed up a little bit, but okay, I'm gonna nick some time of the phased array, of the guided wave stuff anyway. So we also have inline systems, and as you can see, these do not have screens. It's not a thing that you would take under your arm and go into the field. These are systems that are normally used for inline services. So if you have a pipe mill or a car factory, there's many applications where this is used. A lot in the airplane industry, a lot in the automobile industry, producing of pipelines. Basically the same capabilities with TFM, PWI, and even more advanced. But then for a stationary setup. The nice thing about the Panther is that you can stack Panthers together, so you can basically go up to more than 2,000 channels. That's a lot of sensors, and up to 128 aperture. And the aperture is the amount of elements in a transducer that you are going to use at the same time. And a lot of a big aperture means a lot of energy, inspecting, a lot of big wall thickness and that kind of stuff. We also have this on the ZTEC side, which is called the Emerald. Basically, two pieces of equipment that are doing the same. So I'm not going to get into that, but you see a nice example here with the big axle. This is definitely where you need something with a lot of power, a big aperture, and a lot of channels to actually inspect an object like that. Acquire an ultra-vision software. So with advanced systems, you also have advanced capabilities. And one of these advanced capabilities is with the desktop software that are actually could be delivered with a system. That means that if you collect data on your screen, you can analyze it completely offline using that software. You can also create your scan plan. If you make a setup for phased array UT, we call it a scan plan. You can completely, prepare your scan plan offline at your desk, and then transfer that information to the unit that you want it to be used on. Very advanced software with a lot of features, including 3D. Then probe offering, we also have a number of probes. Currently we acquired Sensor Networks. And Sensor Network have a broad range of probes, conventional probes, which you see normally from Kramer or similar, with the advantage of having a short lead time and quite competitive pricing. So please have a look at the website, and you'll see that offering there as well. Also, of course, we have a range of phased array probes. All the phased array probes that you can think of, we produce in-house. Every package that you would require with the appropriate wedges are available also from our manufacturing. And then we have special probes. One of the special probes is the flex array. So if you have curved surfaces, but you will still want to use phased array as an application, the flex array probe is a very nice probe. Also, we have a roller probe. roller probe, normally used for composite materials, inspecting plates and whatever. Now quite a nice combination with the Mantis, and you'll be able to do all kinds of inspection with this roller probe in a tested configuration. So case studies. First of all, this is quite an exceptional application because it's stainless steel, so we're going to use longitudinal waves. And as you can see here, we created a matrix on this area here with using TFM and, or in this case PCI and TCM together. You can see the differences. If we take the images and we compare what we see here, FMC. So there's two things I want to show you: FMC TFM and FMC PCI. As you can see, quite nice high resolution because we use full matrix capture, so we have the highest resolution, quite a number of pixels, 255 kilopixels, and you can see we have a very clear picture of the defects also here on the PCI, but you don't really see a lot of difference. Now if we change the color palettes and we eliminate the noise, then all of a sudden you can see the benefit of PCI also in this application. Here you can see the contours of the block. It's a specially designed block. This is the direction of the cracks, and basically you can see the tips quite nicely in TFM, but even better in PCI. So for instance, this defect here is not so visible in TFM, but it's very visible in PCI. The next example is the difference between FMC and PWI. So again, this is the excitation mode. This is the mode where we are 3 to 5 times faster than FMC. Right? So with 3 to 5 times faster than FMC, you can still see that we have very good results, even though we're 3 to 5 times faster. The amount of pixels is the same, so we didn't cheat there. But the other thing we've done is that we've changed the color palette here again for PCI, and you can definitely see that the smaller defects are standing out. Now, why is this interesting? A lot of applications in the field introduce HTHA or HIC, high temperature hydrogen attack, or high temperature or hydrogen induced cracking. And what that is that there's delaminations or laminations being introduced into the material as it is live, and these laminations have a risk of growing together. And if a lot of these laminations grow together, you get a big defect and a chance of explosion. There have actually been accidents in the field. This will allow you to find and size the smaller defects in HTHA and HIC with quite high resolution, right? So this is a perfect application for HTHA and HIC. Another nice application or a nice benefit of PCI, phase coherent imaging, is that it's not looking at non-coherent reflections. And non-coherent reflections is basically where you look at the top and bottom. So on the left side, you see a TFM image, and very clearly, and a bit annoying, is the red planars, which are basically the bottom and the top of the plate. This is something we don't want to see because we want to see the defect. And in this case, if we use PCI, because with PCI we eliminate the back and the front wall, because the reception of the back and front wall is similar for each individual transducer, we can basically filter that out, eliminate that from the image, and then what we have left is an image with only the defects and not so much with the configuration. So conclusions, TFM and PCI, they're currently complementary techniques. They are in the standards for ESME as well, so if you want to use it, there is a standard for it. You can use both TFM and PCI at the same time, although PCI is not in the current codes. You can still use it to verify defects that you have that you found. And it says here that PCI will soon be introduced with both Gecko and Topaz. I should have changed this slide because PCI is actually already in Gecko and already in the Topaz 64. So this is technology that is currently available with the new software release 4.1. So this is the end of the first presentation. I don't. How far are we over time? We're quite good. Not too bad. Okay. Then quickly, what I want to do is I want to have a look at the. So this is remotely connected to the machine, just to take you through the software and how simple phased array could be. So if you look at the capture software here, then at the top you can see. I don't know if this is visible. No. This is not visible. Let me see. I need to stop this presentation. Yeah, okay. Got that one. Live from this machine, I'm remotely connected. Like I said, I can do this from anywhere in the world. If this machine would be in America, I can still connect. If this machine is connected to the internet, I can make the same connection. And the way this software, capture software, works is basically it provides you with a guided instruction through the setup. So first of all, you see a number of tabs at the top here. Currently they marked green, so I've been through all the tabs and I've done all the setups. And as you can see here, this is, for instance, the specimen. I'm going to specify what kind of object am I actually going to inspect. Now, in this case, we've used a plate, but I can also use, for instance, a nozzle. And what we have here is an object which is 3D. So I can actually manipulate the way I look at the object. Then if there is a plate, I can enter whether there is a weld or no weld. And I can say, okay, do I want my hazardous zone included and how wide is my hazardous zone? And if I have a very special weld, I can select different weld types. So you're not limited to anything, right? So this will help you set up. The other thing we can do here as well is we can import CAD files. So if you have a 2D CAD files, we can import a 2D CAD file and create a 3D geometry from the CAD file. So that's how you set up your asset that you want to inspect. Quite simple. On the probe side, and the nice thing about this software, it works with libraries, and the libraries basically is here, so I can select the probe. I've already selected the probe because I had to do the calibrations for the setup, which you can see here that it's calibrated. But in the probe selection, I can basically select a whole list of probes, not only probes that are ours, but also Waygate probes, G probes, Olympus probes, you name it. They're there. Or even if you have a probe which is not in there, you can basically create it by filling in the dicing and the wedge information, and this will basically give you the same results. There's a very quick way of doing angle height. I would recommend you to have a look at when we do the demo, so I'm not going to go into this now, but I can show you later how simple it is to do a height and an angle calibration. This is obviously quite important for the correct locating of a defect. Anyway, a lot of options there. In this case, we're using a scanner. Again, I can turn the scanner on, I can turn the scanner off, but also we have a full list of scanners, not only Eddyfi scanners, but also Gyra scanners or Phoenix scanners, whatever you want to use. As you can see here, the buttons are now green. That means I can go to the next setup, and basically this is where the magic happens. So first of all, we have the focal laws. The focal laws I can set for each individual probe, and the focal laws will basically allow me to look at the data in real time. I can zoom in on certain areas, I can zoom out and also rotate if I want, making sure that the coverage of my weld is always correct, hitting my weld with the right set of arrays. So here you can see how my setup is currently constructed. You can see I'm very sensitive in this middle area where it's green, and I'm less sensitive in the other area. I will see if I can make that a little bit larger. And then, so here you can see the weld. I'm almost hitting the weld bevel with all green rays. That means that I have almost optimum reflection of that specific defect for that specific ray. And as we said here, we're using currently 38 up to 72 degrees for angles, and we continuously steering that beam, right? So we're doing that a couple of thousand times per second. And obviously I can do this for both probes, making sure I have a probe setup on the left, but also, as we can see here, a probe setup on the right. Okay, so for two different setups I have two probes. The other thing is gates. The gates are basically determining what am I saving in terms of data. I'm not going to go into that now. It's not, well, it's very important, but not so important for now. One of the things that's very important is amplitude calibration. This is one of the top features that you'll find with the capture software. So remember that we're using 38 to 72 in terms of angles when we do a scan, a sectorial scan. That also means that when I'm further away in my beam spread, my attenuation is going to be much different from my 45-degree angle. That also means that if I create a TCG, a time-corrected gain, I'm going to have to do this for each angle in my sectorial scan. That will be a lot of work if you have to do this for each angle. We have developed a system where we can do this in one go. You'll be creating a TCG for each individual angle by using the wizard in here. Quick scan, and within 5 minutes you can basically walk through all the time-corrected gain settings, but I can show you this later as well. Then we have a number of settings for configuration on the motion. This is normally when you use a scanner. You can basically set it how you want the motion, what kind of scanner you are, going backwards, forwards, whatever. Display, I will show you later as well. You have a number of screens, and then the recording is how do you want to record data. Now the interesting part is obviously the inspection itself. And currently this is one of the setups that you can create. I'm currently in acquisition mode. And in acquisition mode, here what you see, and maybe I need to explain this, this is the portion of the weld that I'm looking at. You can see it's upside down. But what happens is when we excite the energy, it's basically going to reflect off the bottom and then reflect upwards at the same angle incident. This is not very easy to interpret. I can change this if I want to. So if I click on the image, I can say, okay, let me see how this looks like when I not do a full skip. I can basically change the mirror display. So in reality, this is what you'll be looking at. And you can see here there's a quite nice defect at the root. It is a little bit harder to interpret, so if you look at it in one direction, but you have to imagine that the weld is on the top. So you can see the weld profile here. So the image, the layout, will actually help you. Okay, this is the energy that has been reflected, this is where it's coming from, and this, according to the calculations, is where it is originated. So in this case, it's a root defect. And if you turn the plate over, you can see there's actually a quite nice root defect there. Then in acquisition mode, obviously these screens are black, but if I would do a scan, you could see that the data would be filled. Let me change this back to to the normal. So I'm currently in acquisition mode. So if I would do pull my scanner now, you could see basically the C-scan images. Fill the thing, and maybe we can do a quick scan. So,
We need that slide.
okay. So off, reset that. So it's not going to be the best scan. Obviously, it's a bit of a challenging setup. So I'm going to do the scan here, and on the screen, as I scan, I can see my defects starting to appear in what we call the C-scan. And the C-scan is basically the top view. So now I'm ready with my scan. I can stop the scan and I can start doing my analysis. Now, we have limited time, right? Ultrasonics can be quite complex, and I would probably need a day to explain everything and all the features that we have. But this in a nutshell is what we can do with phased array and advanced phased array. So I hope the takeaway today is, okay, phased array the normal phased array, the conventional phased array, is a perfect replacement for conventional UT, being much more productive. You can increase your rate of inspections by multitude, and your analysis of the data is much more precise because you record the data. I can go backwards afterwards and analyze all the data on the screen. That's the main takeaway here. The other takeaway is, yes, there's very advanced developments in phased array like FMC, PWI. I just want you to know it exists. We can do it. We'll be happy to tell you much and much and much more, but this is not the time and not the audience. Okay, this is it for now on phased array.
If you want to add a few more details about the analysis, we can extend the time because it is a very interesting topic to phased array inspection.
I'm really deaf, Christian. I have no idea what you just said to me.
If you have a few more details to add about analysis, phased array is a very interesting topic for the audience, I believe. So,
for sure.
You can extend the time. It's no worries.
Okay, I don't want to steal the demo time of the other guys. Anyway, so if I stop my scan here, I can say save and analyze, and it asks me to give it a name. I'm gonna not care about the name at the moment, like I do normally, and that's why my machine is a bit of a mess. But
excuse me, Edwin. By the way, you have a lot of information also again on Eddyfi website, where you have all the elements that.
Well, if we want, we can have a quick look at analysis.
Yes, let's go into all the examples.
Yes. Okay. Okay, so there's a number of interesting things for the analysis side. So I've stopped the data acquisition, and I'm now in analysis mode. These screens are fully configurable. This is the way I configure them, but you can basically configure them any way you like. So first of all, we have a number of crosshairs here, and the crosshairs are actually corresponding to where the probe and the location within the scan is. So I can move this around and I can see a defect, for instance here. We've added scan gain. So normally what we do is we do a calibration. On a calibration block we have side drill holes, we create a TCG, so we can always compare the size of an amplitude compared to a known defect. That's why we use a calibration block. In this, normally when you do a scan, you're going to add 6 dBs to be a little bit more sensitive to make sure you find the defect and then do the analysis. So in this case, I'm going to, you can actually take off the scan analysis, decibels, to become closer to the real defect size. So first of all, I told you that we have a number of TCGs for each angle. So in this A-scan view, you actually see the green line, and you see them for both probes. This is called the TCG, the time-corrected gain. And as you can see, the time-corrected gain is different for each angle. So here, this is my optimum angle. For this defect, you can see that the time-corrected gain follows this. That means that at this point, probably the echo has been corrected about 10 dBs, so more than twice the size. If I would take off the 10 dBs, the amplitude would be much less, but we have to compensate for attenuation of the material. That's why the TCG is vitally important for a good setup. But as you can see, within 5 minutes, I didn't show you yet, but I can show you later, we created that TCG for each of the individual angles. This with another system is very difficult. Very time consuming, and with our system it's quite simple. Anyway, I don't want to show off, but it just happens to be one of the great features. Like I said, the cross section will help us to determine where we are in the scan, and as you can see, the scan actually follows, and you can see different defects. So this is quite an interesting area where I say, okay, I want to have a look at how big this defect is, and I want to add this defect to my defect list. With conventional UT, what you have to do, if you find a defect, you're going to have to use the half dB drop method. So you're going to have to use a probe, find the optimum reflection of the defect, move left, so you see half the amplitude drop, and then move right, see half the amplitude drop, and then you have the size of the defect. quite imprecise, but it is the way that this type of defect sizing works. TOFD in this case would be a much better solution to do sizing, but we don't have a TOFD setup here. So as soon as I've identified the defect, what I can then do is I can go to indication, and indication I have two options. I have creation and assessment. So in creation I can say, okay, I'm not going to do it manually, but I'm going to use auto sizing. And auto sizing, as you can see here, I need to look on the screen, is the criteria is currently set at -14 dB. It's a bit high, so it means that it's going to find probably a larger defect size than you would use the half the drop method, because that's 6 dB. But now with the box here, we can enter the defect, and immediately you can see that it says, okay, this is defect number 1, and also it identified it here in my sectorial scan. We'll make the sectorial scan a little bit bigger, full screen. As you can see now, it's red on red, so it's not optimal in terms of the color palette, but you can see now this is the size of the defect that has been determined by the software itself. If I go back to my assessment screen, then now once I've done the creation, I can go into assessment, and in assessment you can see that what type of it. It's in this case I say it's an indication, so I'm going to classify it as an indication. Then the acceptance is pending, so basically it's not been looked at. So now I can do things. I can either accept this, say okay, it's a defect but it's too small and it's acceptable according to code, or it's non-acceptable according to okay, it didn't need to boot completely. It just needed power. Okay, so this is where we left off. Sorry about that. So I've done my creation of the defect, and I'm into assessment. So I'm going to say it's an indication, and the acceptance is pending. So in this case, okay, it's a big enough defect, so I'm actually going to reject that, and it's not acceptable. And then I can move to the defect list, and as you can now see, it is added to a defect list automatically, given it where it is inside the scan, how big the reflection is compared to my reference, to my calibration, and this data is automatically added to the list and therefore added to the report. So while we do the analysis on here, we also create the report itself. I see another defect there, which again I can go to creation and then say, okay, I found but there's another defect in that area. Again, it's locating and boxing it. If I go to assessment now, I'm in indication number 2, so we already done number 1, that was rejected. Number 2, I'm going to say, okay, that one is also rejected, and maybe there's another one. Should be one on the flank somewhere as well. Maybe that one. Not a redefine, whatever. 2. Again, a defect. Into assessment. Rejected. And if I look at my list, you can see my list is growing. As soon as I do the analysis, it's going to give me the full extent of the defect that I found in my scan, and creating the report as we go. Something which makes life a lot more easier. Something you cannot do with a conventional system. Okay, I want to leave it at this. I'd rather give you a presentation on the system itself later on. If you're okay, still awake and still interested, I also have a presentation on guided waves. So we're going to move to guided waves. Okay. Okay, guided waves. So, as I've shown you in the other presentation, guided waves is also an inspection technology in the family of UT inspections, but much different. Not only different in the way we use guided waves, but also different in the capabilities and the waveforms that we use. Although there are similarities, it is different. Guided waves behave different, and there's a number of things where we have to that we have to take into consideration. So what we have here is a setup with a magnetostrictive tool. The magnetostrictive tools are quite unique. I will tell you a bit more about that later. But basically allow you to also do inspection on smaller diameter piping, shorter sections with high resolution. So where with normal UT, we excite the energy into the material perpendicularly. Here we're going to do it longitudinally. So we're going to shoot energy. Let me get that pointer up again. We're going to shoot energy in the direction of the pipe. Not only in this way, but in both ways. So if I center my collar there, my sensor there is going to shoot energy in both directions. So it's in terms of productivity, it's quite high because we can look at a large number of pipe surfaces in one shot. What's going to happen is that this is a pulse ecosystem. So the collar here is going to excite energy of a certain frequency and a certain wave type, and that is going to reflect on something. So first of all, it's going to reflect on welds, it's going to reflect on defects, and it's going to reflect on pipe ends. If a pulse reflects, there is a difference in the way it reflects. So if it reflects on a corrosion area, let's say, which is on the bottom side or on the side, the returning signal is not going to be axisymmetric. So that means that the reflection is not going to be the same all around the circumference. And that results in what we call a flexurial and a vertical flexurial and a horizontal flexurial mode. That's why with this technology we can do focusing and determine in where on the pipe this defect actually is. So first of all, I'm going to get a reflection of a weld. I'm going to get a reflection of a pipe end, and I'm going to get the reflection of defects. Welds and defects in this case are valuable because we kind of know how the signal responds when it hits a weld or when it hits a pipe defect, pipe end. So when it hits a pipe end, we know that 100% of that energy is being reflected back to the collar. So we have a reference point at a distance and a known excitation point, meaning we can calculate what we call a DAC, a distance amplitude curve. Much similar, well, it's the reverse of a TCG. The other thing that's going to reflect is a weld, and as we know, pipes are being produced in 6 meters, 8 meters or 12 meters length, so we're going to use that weld actually because we know that a good weld actually reflects about 20% of the energy. That also means that we can either use a pipe end, a flange, or we can use the welds to set a distance amplitude curve. Why is a distance amplitude curve important? It's important because we want to know how big that defect is, how big that response is. A response very close to the collar could have an amplitude size of 100%, while the same size deflector at 20 meters away could maybe only be 20 or 30% in terms of height. But still, these are the same defects. And that's why you have the distance amplitude curve to actually determine how that works. This is how a scan looks like. I have better examples and we can show you on the pipe as well. First of all, the black zone here, the blue zone here is what we call the dead zone. Because we use quite low frequencies, the dead zone can be rather large. So if you look at normal piezo-based guided wave systems, center frequency is about 48 kilohertz. Meaning the dead zone can be up to a meter, which is quite large. With the higher frequency, we have a 128 kilohertz here. The dead zone is relatively short, about 30 centimeters. And also because we use higher frequencies, we have high resolution. And what the benefit of that is, I will show you a bit later. But here you see a typical response from a pipe end, external corrosion, and this technology basically detects both internal corrosion and external corrosion. You just cannot say whether the corrosion is internal or external. You're going to have to use other means because we consider this as a screening tool. This is the distant amplitude curve. We have the 0 dB DAC, distant amplitude correction. That means this is 100% of my energy. All the energy that I send in is coming back. There's no the loss attenuation has a certain rate, but it's 0 dB distance amplitude. Then there's a few lines under that. It's the minus 12, the minus 18, and so on. Until you reach a lower level below, you can basically consider this as noise. There are a few wave modes that you need to take into consideration when you excite guided waves. You can use longitudinal, you can use torsional, and what you'll be getting back from these is called flexurial modes. This is basically an animation of how those modes work. So you can see that the L wave is doing this. It's pushing the wave forward. Then there's the T mode, the torsional mode, and you can see the 0.1 is the mode that we're in. So these also exist as higher orders, which we want to avoid because then the velocity of the wave is going to change and we can no longer determine where the reflection of that defect is coming from. So longitudinal is one mode you can use, but we don't use that anymore because it has a few complications when you want to assess the data. So what we mainly use is the torsional mode, a mode which we create with a shear. And what we get back is what you see in the lower, the F1, is the flexurial mode, and this is something that we're gonna assess. And then all of these consist at a single mode at every higher order mode, and that's when you get a pattern like this. And then it's become very difficult to analyze the data. So what we need to pick here is a wave mode which is non-dispersive. And dispersion in wave modes means that the velocity is going to change frequency over thickness. So if the thickness changes, the frequency, the velocity is going to change. And this is something we want to avoid because we want to know, okay, I've shot the signal in a certain direction. We can calculate the time for the reflection and therefore we know the location of the defect. If the signal would be dispersive, anything could have happened in between and we don't know at what time the signal is arriving. So dispersion, staying in a non-dispersive mode is quite important. That's why we only use this portion of the phase velocity to actually excite the modes and make sure that when we get back flexurial modes that we know where they're coming from. Guided waves, they've been around for quite a long time and they were under debate for quite a few years because of the problems or the parameters that influence guided waves. Here you can see what is actually influencing guided waves in general. So a bare metal pipe filled with gas, you can get optimum length in terms of your inspection. That means if I use a piezo collar, not with the magneto, if I use a piezo collar, I could easily get 150 meters or 200 meters in either direction of the collar. So if there is I put my collar here, in ideal situation, there's a defect 100 meters away, I can locate that defect. Obviously not a small defect because I'm using a low frequency and detectability is determined in what we call CSA, cross-sectional area. So this is very difficult to assess. But in this condition, you can get a quite long length. If you go down the list, so you see smooth bonded, you light pitting, heavy pitting, plastic coating, bitumastic coating, concrete coating. In many cases, what we're being asked to do is can we inspect a buried pipeline? And then, yes, this could be done, but is that buried pipeline, is it buried under the ground, has a bitumic masting, bitumic coating, and there's heavy crude oil going to that pipe? Probably not. There's too much attenuation from both the coating and the pipe filling to have any signal left after a few meters. So it's always a matter of assessing what we're looking at, what is the coating type, what's the filling, to be able to determine the maximum inspection length that we can get. So this is a new guided wave system. This is more into the product itself. On the left side you can see the piezo collar. Well, it's rotating, so what's left and what's right. Okay, anyway, it looks quite nice, so I'll move to the next slide. What is quite different about this guided wave technology compared to previous, and we are previous ourselves, because originally this is a product called Tcndt. Tcndt developed with TWI in the UK. Been around for many years. So yeah, all the problems we solved with that system, we have solved with this new system. And why have we solved this? Well, if you go to the field with a guided wave system, you install the collar. You have to do an inspection if there's no corrosion underneath the collar. You do a shot, and then you have to determine optimum frequency. So if you look at the power output and the frequency bandwidth, you want to be in the middle, because there your power output is maximum and your frequency is quite stable. But there is a range. And when you do your shot, you have to, in the field, determine what is your optimum range, and then redo that shot in your optimum frequency. And then when you've done that shot, you need to assess, is there a defect? And if there is a defect, you're going to have to do what is called focusing. If you forget any of this in the old system, you would come home with invalid data. And that's a problem, because you have to go back and maybe the site is not available, the scaffolding is already gone, or whatever the problems are. But what we have now is called full matrix capture. And full matrix capture basically means, okay, we're going to take the data, but we're going to take it for each frequency at every distance of the pipe. That means I can do analysis post the inspection. So really I have to go to the field, put this system on the pipe, take a shot, and I have everything I need. I can go back, do the analysis and see, oh, this might be defect. And then I can change the optimum frequency already there without having to recollect the data, and I can take focus data on that point from the data I've already collected. And this is called full matrix capture. What we've also done is we created the ring spacing. So with the older models, you had different transducers. You could have up to 5 transducers in a row to create different wavelengths, also to cancel out unwanted waves. This is why we no longer use longitudinal, only torsional, because we only have to use 2 transducers. What we also done, we've put these transducers closer together, so we have a broader frequency and a higher power output. Another thing is that we've redesigned the data acquisition unit, so the signal to noise ratio, the SNR, is much higher than what we see with the other systems. So yes, it has a small influence on penetrable length, but maybe not so much. The system now is all-in-one, so you don't need an extra laptop. Everything is inside the module, including the pump. So in order to get the energy inside the material, we need to use pressure. And with the piezo elements, there is a bladder. We're going to inflate the bladder to 60 psi, high pressure, and press those sensors on the material. And then when those sensors start to vibrate, it's going to vibrate the atoms in the material and create the waves. With the magnetostrictive, it works a little bit different. What we're going to do is we're going to create a magnetic domain in one direction within the cobalt iron strip. On top of the cobalt iron strip there is coils, and with the coils we can actually create the motion inside the cobalt iron strip with the pressure, the tension on the collar. We're going to excite that energy into the material. If you look at the system itself, you can see that there's a big touch screen, and you can see that all the units look the same, which means we have the same type of battery, the same operation, the same buttons, which makes it easy to use different kind of equipment because they all have the same functionality. I'm not going to go into the nitty-gritty details of what button is what, but there's USB ports, there's Ethernet, hot swappable batteries, an HDMI port, which we currently are not using. No. So yeah, a lot of functionality there. On the back you see a big cooler casing, so even in the desert you can use this system, or maybe in Romania and the south it can be quite hot as well. I don't know if you have long lengths of pipelines, maybe coming from Ukraine or whatever. So this is an optimum ideal system for inspecting pipelines. The side here, you can see the one connector with the pump valve, the pump connector there as well. And this is the new ring, and I'm going to show you what the old ring looked like. So this is the old ring. You can see that the old ring had different modules. There's a bladder in there as well. We do exactly the same, but there's all this wiring outside. So what you'd have to do is you have to determine, okay, how much sectors do I need? It's octans. How much octans do I need? And then you have to wire each of the octans and test the octans, and quite a lot of work and prone to error, because if a cable breaks, then obviously the system doesn't work. And all of that has now been designed into the collar itself. So you can see a one-point connector here at the top. It's basically click, stick that connector in the collar, click, stick it in the data acquisition unit, and you're ready to go. It's a quick release system as well, so you can see a handle there. Basically take the handle, put it on, and it's in position. You put the pump connector there, you press system to make a measurement, automatically it starts pumping to the right pressure, and off you go to make a measurement. These modules you can take out quite easily. So this is the modules, the black part. You can click them out on the side. You click, they come out, and inside the module there is the two piezo transducers. All right, and like I told you, with the optimum ring spacing that we need for better performance. The other type of collar is the magnetostrictive. So the magnetostrictive, like I told you, works with a cobalt iron strip. But this is a high value for small diameter pipes. You can imagine if you have a transducer which is this wide and you have a small pipe, you can only fit 3, 4, 5 transducers around the circumference, giving you low spatial resolution. But what you want is high spatial resolution. So now with the cobalt strip we use coils, and we can decide ourselves how big the coils are. So now we can get optimum spatial resolution around the circumference using the magnetostrictive for the small diameters. The other thing is that you can create magneto tools in much higher frequencies. So where the piezos are limited around the 48 kilohertz range, we can now go up to 128 as the center frequency. That means we can work from 100 to 145. And because of the high frequency, we have a much smaller wavelength and a much higher resolution. That means if you look at that pipe, we have 1.5 millimeter true holes drilled in the pipe, but we can still see the holes individually with the magneto collar. Why is this interesting? Previously, if you have a refinery, there's a lot of short section pipe work. There's a pipe work of a meter of 2 meters or 3 meters, and then there's an elbow, there's a flange, there's a reducer. This in the past was not possible to inspect with guided waves. First of all, the frequencies were too low, the dead zones was too large. You simply did not have the resolution. With this, with the magnetostrictive, you have the high resolution and the high spatial resolution. So you can now inspect very small defects in short sections of pipe. So in a refinery, you can now say, hey, I have all these pipes going through a vessel or whatever, and you can very quickly, because a shot only takes about 3-4 minutes, very quickly inspect those pipes and screen them and know if there is corrosion in there or not. Now, as I told you, it's a screening tool. So the screening tool will actually mean, okay, I found a defect. You really don't know what it is. Is it inside? Is it outside? So you're going to have to use phased array UT, for instance, to do a follow-up and examine the defect that you found. This is typically what a report looks like. is created on the go. So as soon as you start the system, you fill in the inspection details, it's going to create a report in the background. Then when you do your analysis, and this is a nice example of an analysis with a focus plot. I can show you in a demo later how that works. This is also automatically added to the report. Basically meaning again you create a report on the fly as you go. What's also quite nice is that in the past you had quite a lot of equipment. You had the cables, you had the collars, you had the modules, you had the laptop, whatever not. So you're always with two people in the field, difficult to install, one has to hold it and the other one has to do this and the other one that. Now it's a one-man job. All you have is what my good colleague Sean is carrying here, is a collar, a cable and a data acquisition unit, regardless of the size. Right? Also quite interesting to know, you can use this technology up to 72 inches in diameter. Not in one go. The single largest size collar is 42 inches from the top of my head, but you can combine multiple collars together, tell the system, okay, I've combined collars, we're now up to 72 inch, and do a shot on a 72 inch pipe. So that's quite nice. I already spoke about much of this. So this is basically in terms of the presentation that I can show you. Like I said, there's not so much, well, there's a lot to guided waves, but the system has made guided waves immensely simple. That's why we kept this presentation immensely simple and hopefully understandable on where the technology can be used, how efficient it is to inspect pipework, cross-country pipework, also buried pipework, but especially with the magnetos for the smaller sections in refineries, in chemical plants or fertilizer plants, whatnot, and get very good data very quickly with very simple tools. Okay, I know it was a lot of information. I hope most of it sticks. So I say, hey, let's go with the demos.
Yes, thank you very much, Edwin. Very interesting topics. Și acum ultimul subiect, last but not least, și mă bucur că avem mulți studenți în audiență, pentru că e un subiect de interes pentru cei care vor să activeze în domeniul pe viitor. Invit pe domnul Crişan să prezinte cerințele pentru calificarea și certificarea personalului energiei.
Mă numesc Horea Crişan, în prezent sunt manager pe Tcndt și metrologie în cadrul companiei Emerson și de asemenea acționez în cadrul Asociației României de Examinări Nedistructive. Partea asta reprezintă o colaborare pe care o avem atât cu firmele de control nedistructiv, deci care sunt furnizori de echipamente de control nedistructiv, cât și cu Asociația Română pentru Sudură, cu care avem împreună câteva evenimente, inclusiv un eveniment care va avea loc anul viitor în primăvară. Fiindcă avem câțiva studenți, o să avem și o parte de introducere în ceea ce înseamnă examinarea asta nedistructivă, cât și pentru cei care deja activăm în domeniu, ceea ce înseamnă tranziția la nou standard de certificare și calificare personală, 9712 din 2021 standard european sau 2022 standard românesc. În primul rând, de ce trebuie să efectuăm aceste examinări sau teste nedistructive? Ele fac parte din procesul de calificare și certificare a materialelor, a structurilor sau a produselor. pentru a monitoriza calitatea lor atât în procesele de producție, cât și ulterior în inspecțiile curente în timpul funcționării echipamentelor. Și aceasta fiindcă nedetectarea la timp a anumitor defecțiuni sau defecte poate să conducă la anumite accidente care au loc. Am exemplificat 3 tipuri de accidente care au avut loc în decursul anilor și care au dus, din păcate, inclusiv la pierdere de vieți omenești. Un asemenea incident este la o platformă marină care a fost cauzată de o fisură de oboseală la o sudură necorespunzătoare de 6 mm lățime. Adică concluzia este că la inclusiv o componentă mică dintr-un ansamblu mare poate să ducă la asemenea incidente. O altă sădură necorespunzătoare la un pod care, din păcate, s-a soldat cu 32 de persoane. De asemenea, explozia unei platforme petroliere, aici din cauza că nu s-a raportat la timp un incident și anume deformarea sub presiune a materialelor. În standardul de certificare sunt prezente o serie de metode. Am evidențiat cu verde metodele pentru care există traininguri, cursuri specifice și certificare pe piața din România. Și anume avem examinarea cu curenți turbionali, examinarea magnetoscopică sau cea cu particule magnetice, examinarea cu lichide penetrante, radiografică, ultrasunete și examinarea vizuală. O scurtă trecere prin fiecare tip de metodă. Examinarea cu curenți turbionali se bazează pe principiile inducției electromagnetice și este folosit pentru a evidenția sau a detecta defectele de suprafață și din interior aflate în apropierea suprafeței materialelor conducătoare. De asemenea, este utilizată pentru măsurarea conductivității componentelor metalice, precum și pentru măsurarea grosimii unui înveliș neconducător, cum ar fi vopseaua, bineînțeles aplicată pe un material care are aceste proprietăți. Metoda de examinare magnetoscopică sau cea cu, cum mai este cunoscută, cu particule magnetice se bazează pe proprietățile pieselor de a putea fi magnetizate. Aici ne referim în special la piesele de oțel carbon. Magnetizarea poate să fie directă sau indirectă și putem să punem în evidență imperfecțiuni sau discontinuități de suprafață sau închise sau deschise la suprafața materialului. Aveți o exemplificare a modului în care point-ul pe asta. Ups. Nu merge nici cu mouse-ul. Lasă-mă așa. A modului cum interferează liniile de câmp magnetic în imaginea stânga-jos, în prezența unei discontinuități, precum și particulele magnetice. Vedem că acolo unde avem o asemenea discontinuitate sau întrerupere în material, avem și o întrerupere a liniilor de câmp magnetic, iar particulele magnetice, care de fapt sunt o pilitură de fier foarte fină, se adună în acel loc, punând în evidență defectele respective. Avem de bază două metode de punere în evidență a lor, o metodă fluorescentă, care folosim o lumină ultravioletă, și o metodă de contrast culoare. Examinarea cu lichide penetrante se bazează pe proprietățile de viscozitate a unui lichid și pe cea de umectare a suprafeței. Ea este indicată atunci când urmărim detecția unor imperfecțiuni ce au o deschidere la suprafața materialului. Se aplică un lichid penetrant care se lasă să acționeze pentru a intra în discontinuități o anumită perioadă de timp, după care este îndepărtat și se aplică un developant care extrage lichidul penetrant din discontinuitate, punând în evidență defectul sau discontinuitatea din material. Ca și în cazul examinării cu particule magnetice, avem examinare în lumină ambientală prin contrast culoare, cât și în lumină ultravioletă. O altă metodă, de data aceasta mai complexă, examinarea radiografică, care se bazează pe radiația X și fasciculele gamma, care, după parcurgerea materialului pe care vrem să-l examinăm, impresionează filmul radiografic sau detectorul digital, creând o imagine a materialului pe care l-a parcurs. Pe piață acum avem două tipuri de examinări. Examinarea cu film clasic, care este cea mai utilizată încă în România, precum și radiografierea digitală, atât cu plăci fosforice, cât și cu detectori digitali rigizi. Examinarea cu ultrasunete se bazează pe energia ultrasunetului, care se introduce și se propagă în material sub forma unor unde mecanice generate de un palpator ultrasonic. Dacă aceste unde întâlnesc o imperfecțiune, cum ar fi o sudură, energia sunetului se reflectă parțial sau total pe suprafața imperfecțiunii. În dreapta jos aveți în primul ecran cum arată un semnal care nu este întrerupt de nicio imperfecțiune în material. Avem două indicații, unul provenit de la pulsul inițial și al doilea din de la ecoul peretelui din spate, iar în al doilea cadran avem un puls intermediar care este provenit de la o indicație aflată în material. Și ultima metodă, de fapt nu ultima, ar trebui să fie prima pentru care se efectuează înainte de orice alt tip de examinare nedistructivă și care este cea mai utilizată, examinarea vizuală. Este poate cel mai ușor de pus în practică din punct de vedere al costurilor, dar este una din metodele care necesită o bună experiență a tehnicianului pentru detectarea și încadrarea indicațiilor. Ea se poate face direct, cu ochiul, fără instrumente ajutătoare. Pentru cavitățile unde nu avem acces direct cu ochiul, se pot utiliza videoboroscope, așa cum avem și aici un echipament prezent. Ca și niveluri de certificare pentru personalul care efectuează examinări nedistructive, avem 3 niveluri. Începând de la nivelul 1, cel mai, zicem, cu mai puține responsabilități și de unde trebuie să începem, până la nivelul 3, care este nivelul cu cele mai multe responsabilități și care, de fapt, principala sarcină ar trebui să fie cea de supraveghere și îndrumare a personalului de nivel 1 și 2. Standardul prevede câteva criterii pentru formarea și certificarea personalului. Nu o să le discutăm pe toate, o să le amintim succint pe cele 4. O să insistăm doar pe ce aduce nou ediția standardului din 2021. Avem cerințe de formare și instruire. Pentru cei noi, știți, fiecare metodă sau tehnică, o să vedem că avem și tehnici speciale, există un anumit număr de ore de formare în funcție de nivelul de certificare pe care dorim să-l avem. De asemenea, cerințe de experiență în domeniu. La domeniu ne referim la metodă și tehnică specifică. Avem cerințe de acuitate vizuală și, bineînțeles, cerințe referitoare la examinarea personalului în vederea calificării și certificării. Ce aduce nou, într-un fel, standardul 9712 per 2021, din punct de vedere al cerințelor referitoare la acuitatea vizuală, este că acela că personalul care administrează aceste teste, respectiv vederea din apropiere, verificarea percepției culorii și sau a scalei de gri. Apropo, pentru cei care lucrează, nu știu dacă la vreun asemenea control vi s-a făcut verificarea scării de gri, dacă nu ați cerut-o, cu siguranță nu. Trebuie să fie administrată de către un medic, asistent medical, oftalmolog, optometrist autorizat sau de oricare alt profesionist instruit care este aprobat și documentat de o persoană certificată nivel 3 care acționează în numele angajatorului. Deci nu mai este nevoie ca acea adeverință de acuitate vizuală sau, ăsta să fie un medic oftalmolog. Și poate să fie orice personal de nivel 3 sau un personal care este, să zicem, instruit asupra acestor cerințe, adică nu o să învățăm, inclusiv pe interpretarea mea, inclusiv acel medic oftalmolog, dacă ne dă o adeverință, el trebuie să aibă cunoștințe despre aceste cerințe din standard, cunoștințe care trebuie să fie, să să zicem, transmise și documentate de către un nivel 3, desemnat de către angajator. Am pus aici 3 responsabilități ale angajatorului pe care le-am constatat că, să zicem, se aplică mai parțial în piața noastră. Și anume că chiar dacă persoana este certificată pe un anumit nivel și o anumită metodă, angajatorul trebuie să-i ofere acestea instruire specifică la locul de muncă în domeniul controlului nedistructiv. După această instruire se acordă autorizația de practică, care este o completare a certificării oferite de către organismul de certificare. Am văzut că în ultima perioadă sunt beneficiari care încep să cunoască această cerință a standardului și pe lângă certificarea personalului cer și această autorizație de practică dată de către angajator. Ultima ediție a standardului a introdus, așa cum era și normal, poate că trebuia mult mai explicit să o facă, anumite cerințe pentru tehnicile speciale. Și anume, dacă avem o persoană certificată nivel 2 pe metoda de ultrasunete, acest lucru nu se mai traduce automat, cum era până acum, că acea persoană poate să facă și examinare cu tehnica de phase rate sau TOFD. Pentru a putea să utilizeze echipamentele specifice, să facă o examinare phase rate sau TOFD, este necesar un training suplimentar și o certificare specifică. Diferența se face la nivelul 3, unde acesta este considerat a avea deja certificare inclusiv în aceste tehnici speciale. La fel avem în cazul metodei de examinare magnetoscopică cu particule magnetice o cerință de instruire și certificare specială pentru flux leakage. La fel, metoda de verificare a etanșeității este împărțită în două, în metodă de verificare prin presiune sau cu gaz. Cea mai, să zicem, împărțită metodă este cea radiografică. Standardul cumva a reușit până la urmă să împartă metoda radiografică în mai multe tehnici. În tehnica cu film clasic, cu prescurtarea RTF, digitală, RTD, computerizată, RTC, precum și radioscopică, RTS. De asemenea, s-au introdus tehnicile limitate pentru radiografia cu film clasic, digitală și film și digital în ceea ce privește doar interpretarea imaginii radiografice. Are și o notă foarte clară standardul: tot ce există în momentul de față pe piață, cu certificarea simplă de RT, adică metodă radiografică, ea se referă doar la tehnica cu film clasic. A dat și posibilitatea de a face, să zicem, extindere de domeniu sau tranziție de la filmul clasic la cel digital, scurtând perioada de training pentru nivel 1 la 3 zile, nivel 2 5 zile și nivel 3 3 zile. Dar, bineînțeles, trebuie să existe un examen de certificare în metoda digitală. Un ultim punct pe care vreau să vi-l aduc la cunoștință este faptul că de corespondență între acest standard și directiva 68 din 2014 a Uniunii Europene privind echipamentele sub presiune. Anul trecut, în septembrie 2022, Comisia Europeană a dat o directivă prin care până în luna aprilie 2024 toate organismele de certificare trebuie să facă tranziția la nou standard 9712 per 2022 sau 2021 în ISO. Această directivă de tranziție la nou standard a creat multă confuzie în piață. În acest an, multe organisme de certificare, atât din România cât și din străinătate, precum și organisme de acreditare, au interpretat acest lucru prin faptul că toate certificările, să zicem, existente pe piață sub 9712 din 2013 își pierd valabilitatea în aprilie anul viitor. Da, am avut și organisme care au început să retragă certificările și să emită altele noi după nou standard, deși nu aveau, să zicem, o analiză profundă între vechea versiune și noua versiune a standardului. Am fost în cazul acesta implicat și de-al știu. Am făcut o adresă la Comisia Europeană, în care am explicat punctul de vedere și în dreapta este răspunsul Comisiei Europene, în care sunt recunoscute toate certificările până la expirarea valabilităților, adică cei 5 ani de certificare, doar că după, să zicem, aprilie anul viitor, dacă vrem să facem radiografie digitală, ne trebuie certificare pe radiografie digitală. Deci nu cum să faci, adică până acum că îl face orice persoană certificată pe radiografie. La fel în cazul ultrasonetelor. Deci, asta a fost abordarea celor de la Uniunea Europeană. Asta a fost materialul pe care am vrut să vi-l expun. Dacă aveți întrebări acum sau după, putem să le discutăm. Dacă nu, cred că sunteți mult mai interesați de partea de echipamente și prezentarea lor practică. Eu vă mulțumesc pentru